Hello everyone, this is Behruz and this is pre-recording number 3 as part of the SSET workshop, which is about the practical IEC 61850 for substation automation for engineers and technicians. So basically I'm just going to talk about the basic IEC 61850 architecture. I have already told you a fair bit of that, but I'm just going to continue with what I said so far. So basically, as you understand, as I said in number 2, basically the pre-recording number 2, we need to have an architecture for this standard. Basically, as I said, there are a number of different layers. There are a number of different buses. For example, you have got a process bus, you have got a control bus, you have got a substation bus. This IEC 61850, as I said, is mainly based on LAN or WAN communication. Therefore, it can be based on Ethernet, especially, or TCP/IP, which is totally based on Internet. All right. So what happens is that at the process level bus, what happens is that we have got those field devices, we have got those I/O cards, we have got the memory cards, we have got the sensors, we have got the transducers, we have got the CTs and VTs and all sorts of things, transformers, motors, generators, and everything in there. So we just collect the information at the process bus, then we send it to the control bus, and after that, after process by means of what? By means of a number of IEVs, which can be protection relays, can be controllers, microcontrollers, I don't know, SCADA RTUs or PLC or something. Then the processed information will be sent to the substation bus by means of a data switch, Ethernet switch, and after that it will be compiled and used by means of a substation computer. So that is the thing, that is the how this system works, how this 61850 works. So that is the main architecture of that. All right. So one of the things that comes in between is the method of communication. So I said let's say the concept is the same, but these different users that are somehow connected to substation bus or the process bus or the control bus, they have got different options basically to be connected in terms of communication method. All right. Also, in terms of sharing the information with different buses, what happens is that, again, that sharing the information could be one way or it could be two way. For example, it's more like something like what you have got in a TV, for example. That's one-way communication. Whatever you have got in a radio broadcast, for example, that's a one-way communication. So this is what we say the simplex communication. So sometimes when we are going to send the information between points A and B, it is just a one-way street. So at all the time, point A sends the information to point B without expecting to receive the signal back or the analyzed signal back from point B. So it's more like, for example, the master station for some RTUs, for example, particular RTUs, it is just sending the information, all right, some particular information. So that if that is the case, if that system of communication is required, in that case that will be very simple, that will be very low cost and very easy to understand. But on many occasions this is not the case. On many occasions the nodes, the points on the system need to communicate the information as a two-way street, not just one direction. Okay, in that case you need to have a duplex communication. So that duplex communication could be half duplex or can be full duplex. If it is half duplex, it means that, for example, by the time station A is sending the information to station B, station B cannot send any simultaneous data. They have to wait until the communication is finished by point A, and then they start sending back the information. But if it is full duplex, exactly like what you've got on a telephone, you, for example, talk, the other person talks, so we can talk simultaneously. Even on the telephone, at times you understand, especially for remote calls, you understand that while you are talking, the other person cannot talk, or while they are talking, you cannot talk, all right? They will not hear that. So it's more like a half duplex. But if it is full duplex, the transmission and reception of the information can be done at the same time. It's more like walkie-talkie or two-way radios, for example. So what happens is that when it goes into half duplex, what happens is this. So this is half duplex, for example, right? So half duplex provides communication in both directions, but only one direction at a time. All right, and that's because of what? Because on many occasions they are using the same frequency. So since they are sharing the same frequency, they are not able to, let's say, they use the channel at the same time. But when you look in here, it says it is full duplex. So they are sending the information simultaneously. And that's because of what? Look at the last sentence. Because they are using two different frequencies most of the time. So they have got an F1 and an F2. So this exchange of information is done on two different frequencies. So what is the good thing? So first, what is the disadvantage of full duplex? Well, that is the most expensive of all. So, but are there any advantages? Oh, yeah, many. For example, there are no collisions, and therefore there is no time wasted on the channel. Let's say the channel has got the full data capacity, okay, in both directions, and the stations do not have to wait until others complete their transmission. So that can happen in a, for example, two-way radio communication. That can happen in a telephone conversation, and that can happen in a substation automation system. So when you are thinking about 61850, most of the time you're thinking of a full duplex communication between different nodes if you would like to get the best quality for the 61850, right? So the way these stations are communicating to those data buses should be full duplex, so that at all the time they are allowed and able to send the information to the other party. So that's one of the things with regards to communication. Another consideration is the channel capacity. So I talked that by choosing, for example, full duplex, we are able to make it, for example, let's say we are using the full capacity of the line, of the channel, of the cable, of the bus, all right? But sometimes you have got a lot of signals, and well, they mustn't get confused, of course, right? So you are going to send everything on the same channel. So that'll be confusion, especially if you have got the frequencies pretty much close to each other. So in these cases, what we do is that we calculate the maximum bandwidth of the channel, and we just divide it into a number of slots, okay? And then we put the signals next to each other, so they will sit next to each other within the bandwidth of the channel, and basically that is what we understand. Let's say for the the multiplexing. So this is what let's say that the multiplexing is there, and this is how it works. So therefore, this is the meaning of multiplexing. So we have got one communication channel, and the signals can sit next to each other by means of multiplexing. So it means that we just convert one frequency into a number of sub-frequencies, okay? So for example, we have got the principal basic frequency, and by means of multiplexing, we just create some more basically signals in different shapes, just not to be confused with each other and sitting in the next, in the same thing. So this multiplexing is more like decoding the information, more like encoding the information. So when it is received at the other end, again, it has to be decoded. Okay, so this multiplexing, so the opposite of multiplexing is demultiplexing, or just encoding and decoding, or mux and demux, as they are saying. So if you are going to send all the information on one channel, you have to mux it by means of multiplexes, so that these signals can sit next to each other, being sent to the other party without getting confused, okay? And then by the time they are received at the other end, they have to be demuxed, so you can dismount the main basically frequencies and signals from, let's say, the total multiplexed channel, okay? So this is how it works. Now, in terms of multiplexing, we can do it in two different ways, okay? So these signals should be different from each other, okay? So that multiplexer should make them different from each other, so that they can sit on the same let's say channel. So that can be done in let's say a number of ways. Okay, so there are possibilities that this is done in a number of ways. One of them is in terms of let's say the frequency. So this is what we call the frequency division. So basically what happens is that during this FDM or frequency division multiplexing, it means that we are creating let's say some guard bands, and we're just sending the information at frequencies that are not very far from each other, close, something like 92, 92.2, 92.4, 92.6, as you can see in here. So we just consider, let's say, 0.2 megahertz guard band between each two signals, and these signals can sit on a range, on a bandwidth. This is exactly what is happening in your, let's say, radio receivers. You just change the tuning of the radio, right? So you receive station number 1, station number 2, station number 3. This is exactly it. So the radio station basically put those signals next to each other so that they can receive them without confusion. So this is exactly what we do in a substation automation system, for example, right? So we just put them next to each other with a little bit different frequencies, these signals. And then we can get them back from the system. So this is what we call the FDM. In a much similar way, we have got the TDM multiplexing. So this time, these signals will be deviated, will be different by means of their time, by means of their period, by means of the time it takes for them to appear in the system. So as you can see in here, it's more like we have got a switch. We have got a selector switch in the multiplexer and in the demultiplexer. So we can see that we have got inputs, for example, number 1, 2, 3, 4, 5, 6 something, and we have got the outputs on the right hand side, 1, 2, 3, 4 something, all right? And in between we have got the communication channel. In this particular case, that communication channel is fiber optics, all right? So we have got the transmitter at the left-hand side, we have got the receiver on the right-hand side. So what is happening is that we put these signals into a number of alternating time slots, something like input 1, input 2, input 3, input 4, as you can see in here. So one by one, this selector switch comes in and send the information one by one. So first of all, input number 1 will be sent, and then number 2 will be sent, and then number 3 will be sent. So you can see that between each two consecutive signals, there is a time delay. And that is how the signals will be differentiated from each other. So this technique is what we call the TDM multiplexing. So all I'm saying is that in your 61850 automation system, you have already selected a number of signals to be picked up and analyzed. All right, be transmitted to the other party, again have another analysis, and then again send it back to RTU or PLC or whatever that you have got in there, right? So in order to do that, you need to have a communication channel in between. Whenever you have got a large array of information to be sent to the, let's say, the SCADA master station or something, in that case, they have to be multiplexed. That multiplexing could be based on frequency, or that multiplexing could be based on time. All right. Also, another thing is that while we are doing all this thing, another thing that we do is just to digitize the signal. Normally, the information that we receive from the field devices, from the CT, from the VT, from the transformer, from the motor, generator, the buses, and everything to be analyzed, right? So, most of the time, this information is in terms of analog signal. But when it comes into SCADA RTU, when it comes into SCADA PLC or something like that, in that case, these signals need to be digitized. So you need to have analog to digital converters. And then again, you need to have, by the time it is processed, by the time it is analyzed, again, the information has to be sent back to the field devices just to adjust themselves, okay? If you have got overload, if you have got, for example, monitoring over the pressure and the level of the SF6 gas, for example, if you have got control over, let's say, the temperature of the windings of a transformer or something like that, for all this information at the beginning, they are all analog. So you receive this information, you digitize the information, now you make this transmission and reception in terms of digital signals. which is much easier, much better, a lot higher quality you will gain. So by this way, you will minimize the errors a lot. So you will maintain the integrity of the digital signal. You would be away almost 100% or 99% or something from signal errors. So if you are free from signal errors to a large extent, you can minimize the related noise. Okay, so this is how it works. So we need to do multiplexing. It can be FDM, it can be TDM. We should do, let's say, digital transmission, digital reception. So they are all part of that communication channel that you have got. So what are the advantages of digital transmission? Excellent noise mitigation, improved signal-to-noise ratio, or SNR, very low signal attenuation over long distances, advanced error correction techniques, fast signal transmission and reception, cost-effective switching and multiplexing, and better integration with data and video services. So it depends what kind of information you are going to send to the other party. Okay, especially this noise is of utmost importance, right? Noise on the signal. So what are the things that can create noise on the signal? And then again, it can affect your, let's say, system automation. Either it is the MP3 or it is 61850. This noise is of utmost importance, right? So you need to have absolutely reliable communication link. So even if your, let's say, the protocol is very good, even if your object detection and mapping of information and those, let's say, addressing of information and those packets and packages of information, they are all perfect. Okay, these are the things I've already discussed and mentioned and explained for, let's say, IEC 61850. Those are the things I've already mentioned. Even if everything is perfect, but if you have got some noise in the system as a result of what? As a result of variable speed drives, as a result of, for example, having all this network established in an industrial area where you have got a lot of different noises and signals or something, as a result of pollution in the air, as a result of industrial noise, as a result of many different things. Vibration, for example, of the machines, as a result of the corona and partial discharge of the transmission lines. We have got many sources of noise, okay? So basically by digitization of the signal, we just sort of making it immune to noise. So we have got excellent noise mitigation. And an index for measuring that noise mitigation is what we call the SNR, the signal-to-noise ratio, which is measured in terms of decibel. So that is 10 times logarithm of that signal-to-noise ratio in the base of 10. All right, so that is what we call the SNR, and SNR in terms of decibel should have a minimum acceptable value, so we can accept that thing. So especially in terms of error correction, in terms of, let's say, fast and accurate signal transmission and reception or something, that could be very good. And guess what? In terms of price, also it could be cost effective. So let's say the cost of digital systems these days are a lot less than what we have got for an equivalent analog system in our methods. So basically, when you think about a traditional substation architecture, let's say substation automation architecture, this is how it works. This is very, very important basically to understand in here. So you have got, for example, the protection relays, say relay A, relay B or something like that. You have got the bay controllers, of course, so that not all the responsibilities have been put on the shoulders of the relays, so that you are not going to have a total fail, as we discussed in pre-recording number 2, right? So this while not all the responsibilities have been put on the shoulders of the relays, but have been shared by the bay controllers as well, okay? So, but again, this is not 61850, because this is not object-based. This is not comms-based. This is just asset-based. So you have got the relays, you have got the controllers, you have got the CTs, you have got the VTs, you have got the conventional switchgear or something like that. So this this is how it is working at the moment, right? So I would say 90% of the sites that you have got, they are not 61850, okay? So this is how they have been mapped, they have been modeled, they have been established, they have been architectured, okay? So this is the thing. So in between, you have got something like a station bus, and that station bus can share the information with a number of HMIs and the engineering services. Through router, it can send the information to control center, to other master stations or something. So this is working okay. I'm not saying this is bad, but the issue is this. When you look at the bottom side, you can see that we have got a lot of connections. We need to have a lot of wirings, okay? That is the issue. We need to have a lot of space. We need to have a lot of panels, space, terminations, junction boxes, marshalling queues, panels, and wires or something like that. So, and as a result of that, conduits and trenches and the cables and the data cables and the control cables and a lot of things. So that is the issue. At the moment, the system is working okay, so there is no problem with that. But the issue is that the scientists, the engineers are thinking of ways so that they can minimize the cost, so that they can minimize the cabling work, the wiring work, or something like that. And as a result of that, they can make a saving in time and they can make a saving in cost. And that's why we are trying to make a development in here, something like this. So now you can see that it's more like that example I told you regarding the wireless system. So this time you can see that rather than having a lot of wires and terminations and the cables and things like that, this time we are pretty much similar to the concept of app on your mobile. As I said, now you have got a process bus. Okay, so everything's been modeled, everything is wireless almost, okay, so everything's been saved in there. So you have got some typical templates and the models or something like that. So everything is saved on the process bus, shared on the process bus. So all I'm saying is that from one level or from one bay or from one bus, it will go to another bus. From process bus, it will go to station bus. Okay, so we do not focus on the identity of the assets. We do not insist on the identity of this box, for example, if it is a relay or if it is a controller or if it is what, okay? But we look at them as object, and each object has got its own definitions, has got its own characteristics, and has got its own programming, okay? So we have to look at this thing like that, and if we look at it like this, everything should be programmable, should be able to be modeled, should be able to be put in a mainframe, okay, so that you can say that that belongs to the process bus, or no, this belongs to the station bus, or that can be the input to the station bus, and that can be the output to the station bus. So this is the way you would define an automation system in the IEC 61850. So that is the main aim. In a very similar way, I can show you this. So again, you can see at the very bottom level where we have got the process level, or process bay, or process bus. Again, you can see that we have got a number of, first of all, modern CTs and VTs, like optical VTs and optical CTs in here. And then the information that is grabbed and collected in here is merged together by means of merging units, or MUs. And then the information is sent one layer up by means of communication. That communication, if it is 61850, I said most of the time that communication is Ethernet, which is a kind of LAN, okay, or WAN. So basically it is LAN or WAN based. This is what we call the network, okay? So the sending of the information, which is very quick and reliable and everything like that, so it is based on LAN or WAN, in very particular Ethernet and TCP/IP. So these are the things that are used. Okay, so basically these MUs, or merging units, just publish, as it says in here, the V and I and the status of data sets So these are the publishers. These merging units are the ones who are responsible for publishing the status of the information. Let's say the status of the circuit breakers, the conditions of the CTs and VTs, and the information that is received from the transformers or something. So you are going to automate the substation, is that right? So these merging units are merge this information, put them in different categories and appropriate groups so that you can therefore then identify and again assemble together or just get them separated. Okay, and then one layer up, it will go to IEDs, let's say relays, and after that you have got the station bus. By means of a network, you can also provide remote access to operators and decision makers somewhere else. So this is the model that we have got for the substation automation. All right, regarding that merging units, it says IEC 61850 process bus architecture using merging units to collect what? To collect signals from the CTs, from the VTs, from the circuit breakers, from these kind of things. What kind of signals? Like the process information, control information, status signals or something. So how it works, the IEC 61850 output of each merging unit is connected via pre-terminated fiber cable to a patch panel that directs the appropriate signals to each relay. So this is how it works. To exchange information between electronic current transformer and the bay level equipment, merging unit is introduced. So they are kind of interface. They are kind of facilitators, as you can see in here, right? Just to match patches of information together by means of, let's say, predetermined fiber cables. So this is the thing that you need to have, and this is a very necessary part of the 61850. Right. Also, it says the communication network within the substation is divided into 3 levels. This is what I said before. So we have got the process level, we have got the bay level, and we have got the station level. So the process level includes the switchgear equipment, the actuators, the sensors, the CTs, the VTs, and the motors and generators and transformers or something. And then the process level, the process bus, also communication network between the process level and the bay level IEDs. So that is for the process part, okay? And it could be something like this. So you can see the bay level, you can see the station level, you can see the process level. So the process is the first step. You have got, for example, the HV equipment, you have got, let's say, everything in here, and basically the information is collected as part of the 61850, and then it will be sent to, let's say, the bay level. And in the bay level, you have got the protection and control, and from there it will be sent to the station level, which is consisted of a number of functions. All right. So this is how it works. So this is again the 61850 substation architecture. So in very general terms, you can see this is an example, for example, where you have got, that's such a big site you have got. You can see that at the process level, we have got a number of equipment. Also in there, we have got the CTs, the VTs, the relays, the IEDs, and basically this 61850 has been applied in there. So by means of Ethernet switch, okay, the information is collected from this process level and is dispatched and issued and published to the next level, which is the bay level. In the bay level, again, you have got a number of other IEDs and the RTUs and a lot of things like that, okay? So a further process is done. Okay, so you have got some, let's say, communication embedded computers or something, and basically you need to have processors, and basically after that, again, by means of another Ethernet switch or switches, this information is delivered to the next level, which is the substation level. Now you can see that the graph has been, this diagram has been color coded. So we can see that part of the links are orange, part of the links are green, part of the links are red. So it means that it is not necessary that all the users, for example, are using the same comms media to send the information or receive the information. Well, it can be Ethernet, which is blue or green. It can be fiber, which is orange, or it can be the serial link that is basically, let's say, anything. Let's say RS-232, 485, or TCP/IP, or anything like that. Okay, so they can communicate like that. But as I said, this is the present trend. This is the current trend. Maybe in the future trend may not be like that. The future trend may accept only a globalized, general, let's say, means of communication, and let's say the protocol or something. I don't know. Maybe in the future there will not be any trace of DMP3 or something, just 61850, who knows, just for substation automation system, all right? But at this stage, they are working all together pretty much conveniently, right? So we have got the communication processor, we have got the back-end communication host, and all these things are there until the time all this information is delivered to the control center at the very top. In a very similar way, you can see another site. Again, you can see the VTs, the CTs, and this time you can also see the merging units. So they are just merging all this information together, and then again by means of Ethernet switches, they let's say this deliver let's say the information to the next level. But what has been also added in here is some kind of let's say a time synchronization. You can see that we have got a clock. It's a satellite clock. So it's very important that in terms of the timing of these signals, everything is perfect, so that all these stations and the receivers and the transmitters have got the same information and understanding about the time the signal was sent or the time the signal was received. So it is very important, this time synchronization between all these levels, it is very important. Then again, the signal is delivered to the bay level. Again, you can see that we have got the protection relays, we have got the IEDs and everything. And again, you can see that we have got different forms of communication. Again, it's been color-coded. You have got the optical fiber, you have got the Ethernet, you have got the serial. So you can see that again, the information goes to the next layer like the station level, and then again, you have got some further processes in there. So, well, we can use different processes from different companies. American companies, Canadian companies, German companies, Japanese companies, Chinese companies. Well, we have got different processes, we have got different functionality. They are not, of course, exactly the same, but the concept is the same. Let's talk about that, the station bus at the very top. So what about that? We already know about the process bus. Well, what about that station bus? The station and bay levels, normally they come together. As I said before in pre-recording number 2, protection and control normally occur in station level and bay level, right? They are connected via station bus, and it provides primary communications between the logical nodes, which provide various station protection, control, monitoring, and login functions. Wow. So all I'm saying is that if by means of any reason, if you just lose any of those logical nodes, in that case it is pretty much likely that there will be some errors in terms of protection, in terms of the control logic, in terms of your monitoring, metering, measuring, login, things like this. All I'm saying is that these logical nodes have got identity like a person. Okay, you are going to model these logical nodes, so you have to attribute I don't know, some kind of identity to these nodes. This identity could be in terms of many different things, okay, like that multiplexing and demultiplexing that I told you. So you need to have some parameters for these nodes to define. And as a result of that definition, you as the system designer will program the system. So when you say I am in the business of programming 61850, it means that you are first of all understanding the identities and attributes to each node, and then your knowledge base is like you have got the capability of mapping all this information into this station bus in the language of the machine. not in the language of the human. By means of HMI or whatever that you have got in between, you have to interpret that information in there. So if your model is wrong, if that language is wrong, if the attributes are wrong, in that case, things go wrong, and you will have, of course, error in between. So that is a very, very important layer. So, but in between, from this layer to that, from this level to that, you have got communication. So it says communications will operate on a connection-oriented basis. For example, request of information configuration, a connection-less basis, IEC, generic object-oriented substation level of GOOS. The station LAN connects all of the IEDs to one another and to a router or other device. So as I said, this IEC 61850 is based on big networks such as wide area network WAN, or at least a LAN is required to, let's say, demonstrate the functionality of this 61850. So that was for the station bus. What about the process bus? One more time. This bay level and process levels are connected via the process bus. So put it this way, we have got a number of levels and we have got a number of buses. We have got the process level, and we have got the bay level, and we have got the station level. Okay, between each two level, we have got a bus. So it says between the bay level and the process level, who is the connector? The process bus. Between the bay level and the station level, who is the connector? The station, let's say the station bus. So these buses are data buses. Very, very important. They convey unprocessed power system information. Conveyors. They just convey, they just exchange the information. It can be voltage or current samples. It can be circuit breaker status, for example, whether it's open or closed, or disconnect switch or anything. You are talking about substation automation, is that right? So you should be aware of the status of the circuit breakers. You should be able to remotely control the status of the circuit breakers. Even at times, if your disconnect switches are motorized, you should be able again to at least understand the status, whether it is open or closed, and if they are motorized, just to control whether they just remotely open or close them. But at least the status is important. On many occasions, the operator, the designer, the engineer needs to know what is the status of this switch. Is it already open? Is it already closed? So they can define a logic, so that later on they say, if it is closed, blah, blah, blah. If it is open, blah, blah, blah. So it's something like that. So that is the idea for this 61850. So we have to define a number of logics. So one more time, when it goes into the substation architecture, this is a little bit of repetition from before, but again, it's worth it. So you can see we have shown here the station bus and the process bus. From the very bottom, you can see the process level, and then you have got the bay level, and then you have got the station level. But what are the connectors? Look in between. You have got the process bus, and you have got the station bus. We are not talking about the power bus. We are talking about a data bus. So in this case, the process bus is a LAN, and also we have got the station bus. So this station bus can be connected to, let's say, a gateway, so that it can share the information via a network remotely with others. At the same time, you can directly connect your laptop or your desktop computer to that station bus if you are an operator, if you are a decision maker, if you are an authorized person, and to see what is the status of your system regarding all the pumps and the tanks and the, let's say, the conveyors, and regarding all the generators and motors and transformers or whatever that you have got in here. The person who is sitting close to that HMI screens will see all the status, whether this valve is open or closed, whether that switch is open or closed, whether the, let's say, the height of, for example, the liquid in a container is this much or that much. So they will have the visibility to everything. All right. So again, as I said, this 61850 has got a number of parts, part 1, 2, 3, 4, something like that, and some parts of that is, let's say, referring to that the process bus standard. So it says has only been applied in some pilot installations. So it's not been well developed yet. And benefits of process bus. So reduction of the copper wiring requirement to interface to the process equipment, digitalized information system, automated testing is possible, which makes the implementation procedure easier. So once again, I will get back in here. So this process bus is of utmost importance, right? So that is the whole idea, the major idea for this 61850. You are going to make some savings in the cablings and the wirings and the labor hours and the complexity. You want to simplify the information or something like that. So a large effort is just put on the shoulders of the process boss, as you can see in here, regarding digitalizing the information, regarding digital transmission, regarding, let's say, the reduction in, let's say, the wiring or something. It's more likely to be at the process level and process bus. I told you also that the substations that are automated under 61850 can be categorized under centralized stations or decentralized stations. Okay, so either they are centralized or not. So if they are centralized, they are characterized by having only one central element for computation, data storage, and communication. Is it good? Well, in terms of simplifying the work, yes. In terms of saving a lot, in terms of wiring or something, yes. Is there any danger with that? Yep. If you lose that center, you're done. Finish. Okay, so the RTU is the single access point from the NCC, and all applications are executed in the RTU, and all data from the process are brought to and stored in the RTU. So that is the centralized. If it is decentralized solution, no. In that case, they have HMI and a gateway on the station level, or protection and control units on bay level, a conventional interface to the process level. So it's not centralized in one point. Some of it is at the location of process level. Some of it is at the location of the bay level. Some of it is at the location of the station level. So it's been scattered. It's been distributed. Okay, it's not just centralized in one place. The control and protection functionality is located on the bay level. The gateway is the single point of remote connection. Well, as long as you are keeping your gateway, those buses or something, everything's fine. Okay, because it's not been dumped and centralized in one place. Again, regarding that decentralization, we have got some, let's say, derivatives. It says decentralized PB solution or process bus. Okay, so let's say not for the whole system, not for the whole IEC 61850, but just for the process bus, we can have it decentralized. It says it is the same as the decentralized solutions, but it has a process bus for the connection between the bay and process levels instead of the conventional interface. See, even you have got another bus again between the two bays. The process bus connects to intelligent sensors like electronic sensors on the process level. All I'm saying is that by adding these on and on and on and on, you are minimizing the effort in terms of the wiring and cabling and all sorts of things, which is pretty much good. But at the same time, remember, you are adding to the complexity of the system. You are adding to the logic of the system, all right? And lastly, you can see, let's say, another, all these things, centralized and decentralized, and also decentralized process bus examples in here. So you can see that if it is centralized, it is pretty much easy, and everything's been compacted in one place. However, if you lose that center, very bad news. If it is decentralized, well, it is not as bad as that, so you have got a little bit more relief and comfort in here, but at the same time, you need to have a lot more cabling and, let's say, more devices. You would need to have some more space. And also, again, decentralized just applies to the process bus. You can see that again there's more comfort in terms of redundancy, but in terms of the, let's say, the work itself, well, it costs you more, and basically more wirings, more complexity would come with it. Okay, thanks very much for listening to me. This is the end of pre-recording number 3, and I hope you have enjoyed it with me. Thank you guys, and I'll see you in pre-recording number 4. Thank you and goodbye.